Let's take a look at the types of proofs that we're going to use in this course. But first, a word about proofs in general. A proof is a compelling, logical argument that some statement is true, or in some cases that a particular claim is false. The proof must be convincing. There can't be any holes or loose ends in it. Each step needs to follow from the prior step, and each step must be clearly established as being valid. But above all, it must be absolute. There can be no room for doubt about the validity of the proof. We're not trying to prove that something is true beyond a reasonable doubt. We're trying to establish that it is true beyond any doubt, period. We'll be using three types of proofs in this course: proof by construction, by contradiction, and by induction. Proof by construction, for us, also covers what are known as direct or deductive proofs, in which axioms are used to walk from the beginning to the end. But more often than not, we'll be doing true constructive proofs where a claim is made that something exists or something can be done, and we describe how to build it or how to do it. Proof by contradiction is a very powerful tool and usually involves assuming that what is claimed to be true is actually false. The goal is then to show that this assumption leads to something that cannot be correct. As long as the only assumption that was made was that the claim was false, we can then conclude that this assumption was wrong and that the claim is actually true. Proof by induction is probably the most powerful form of mathematical proof. Unfortunately, it only works for situations where things scale in discrete increments. We first show that the claim is true for the smallest size instance, and then, assuming that the claim is true for some arbitrary size, we show that it must also be true for the next larger size. The idea is that if we prove that we can go from k to k plus 1, and if we've proven it for, say, k equals 1, then we could walk up on a step-by-step basis and show that it is true for k equals 2, 3, 4, and on up to whatever size we care. So let's look at a simple example of each of these types of proofs. A very simple proof by construction task is proving the claim that a 2 graph exists for any size graph that has at least 3 nodes in it. Recall that a k-graph is a graph in which each node in the graph has a degree of exactly k, meaning that it has exactly k edges connected to it. The proof involves describing how to construct a 2 graph for any value of n greater than 2. We'll do so by arranging the n nodes around the perimeter of a circle, and then we will connect each node to the 2 nodes on either side of it. Since n is strictly greater than 2, these 2 nodes will be distinct. That's why we require n be greater than 2. This node obviously has degree 2, and since each node's edges are connected this way, every node in the graph is going to have degree 2. For proof by contradiction, we'll use the claim that there are an infinite number of primes, or stated another way, for every natural number, there exists a prime number larger than that natural number. Here we will assume that the claim is false, and that there are a finite number of primes and therefore some largest prime. We will then set the value p equal to the product of all primes, and we will set q equal to 1 greater than p. Since q is greater than the largest prime, it can't be prime, and thus is divisible by at least 1 prime. That prime must also be a divisor of p. If any 2 numbers have a common factor, then their difference also has that same factor. Hence, q minus p is divisible by some prime. But q minus p is 1, and 1 is not divisible by anything other than 1, which is not prime. Here's our contradiction. Therefore, the assumption we made that there are a finite number of primes must be incorrect, from which we can conclude that there are an infinite number of primes. Proof by induction is a 2-step process. So here we're going to prove that the claim that the sum of the first n natural numbers is n times n plus 1, that all divided by 2, by first establishing the basis, using the smallest natural number, 1, as our starting point. Clearly the sum of 1 is just 1, and this agrees with the result yielded by the claimed formula. This establishes the validity of the basis. Next, we'll assume that it is valid for some arbitrary natural number k, and then show that by directly applying the meaning of the claim, we can manipulate it into the form of the claim. If S of k is the sum of the first k natural numbers, then we get the sum of the first k plus 1 natural numbers by simply adding k plus 1 to S of k. We then write S of k according to the claimed formula, and then recast it into the same form, except using k plus 1 instead of k. Having done that, we can conclude that the formula is actually correct for any value of n. So let's wrap up our discussion by talking about some of the common mistakes people make when crafting a proof. First, when doing the induction step, you can't use a specific value of k. Doing so would just prove that it works for that one value. You must instead leave k as an arbitrary variable in order to show that the proof holds for any value of k, be it 2 or 2 trillion. Another common mistake is to unwittingly perform a proof by example. This is valid only if the claim is that at least one thing exists, but not if the claim applies to an infinite set of things. For instance, let's prove the claim that x squared is equal to 2 times x for all natural numbers by showing that if x is equal to 2, since 2 squared and 2x are both 4, the claim is true. Obviously, this is a invalid proof. All we've actually done is shown that the claim is true for the specific value of x equals 2, not for any natural number x. Another thing that trips people up is they'll do something that is intended to prove that something is false, and failing to do so, conclude that it must be true, thinking that that's the only other option. But there is another possibility, and that is that it actually is false, and we just failed to prove it. For instance, a true fact is that all birds procreate by laying eggs. So if we prove that a particular animal species does not lay eggs, we've proven that that species is not a bird. But what if we prove that the species does lay eggs? Does that prove that it is a bird? No, it could be a crocodile. Laying eggs may be necessary for the species to be a bird, but it is not sufficient.